So I will. So we started with the register allocation problem in the last class, and we discussed how to do register allocation within a basic block that is called as local register allocation algorithm. The main idea behind register allocation uh, is we would like to promote variables to registers in such a way so that the traffic to the main memory gets minimized, because main memory access is or a bottleneck. The speed, given the current technology, the speed at which the processor can do computations, the main memory will not be able to supply data at that rate. And so you try to keep the values as much as possible in the registers, and the next best thing that you can do is you try to do program transformations in such a way so that the current working set size of the program remains in the cache memory, preferably in the L1 cache, L2 cache, LLC, last level cache. So you would like to do program transformation so that data that you are going to access in the near future, it is available in the cache. But the approach that we take for register allocation and for program transformations to utilize to maximize cache utilization, these are completely different. And our focus into today's lecture is on register allocation, where we would like to come up with an algorithm to promote variables to registers in such a way that traffic to the main memory gets minimized. That is the goal. In the last class, we have seen how to do this at a basic block level. The first idea that we have seen in this context is that you have let's say this is a basic block. So this is your basic block. So the property of a basic block is it's a straight line sequence of code. Uh, the variables are promoted to virtual registers. Let's say a variable X could be allocated a virtual register VR1. So another variable Y could be allocated virtual register VR2, so on and so forth. And when the code generation module assumes that that there are infinitely many registers available, virtual registers available, and generates code. And then we have to rewrite this code by mapping these virtual registers to physical registers in such a way that, so, and then, so after this mapping is done, we have to rewrite the code so that the generated code is ready for execution on the target machine or the processor. We have seen a couple of simple approaches. One simple approach is you look at the frequency with which different variables are used. And let's say X is used with the highest frequency, and Y is used with the next highest frequency, and Z is used with the next highest frequency. And let's say if there are only two registers, two physical registers available, then so X is present in VR1, so and this so and VR1 is mapped to register R1, and Y is uh, present in virtual register VR2 and it is allocated R2, and Z is present in virtual register VR3 earlier, but now it is present in mem. This is the idea. So since the variable Z is present, is not allocated any register, so we say that the variable Z is spilled. So we say spill Z, spill variable Z, spill variable Z. And when we spill variable z, so we have to, wherever variable z is accessed in the basic block, there we have to insert a load instruction to read the variable z from the memory into some scratchpad register to do the computations. And wherever there is a store or write to variable z is there, that is wherever variable z is occurring on the LHS, after that instruction, we have to insert a store instruction to move the contents of the value into the memory location corresponding to variable z. And these load and store instructions that we insert in order to take care of variable z, this is what is called as a spill code. So the particular allocator that we talked about, it is what is called as a top-down allocator, where we allocate registers to variables based on the frequency with which the variables are used. Okay, so first is top-down allocator. We have seen this in the last class, top-down approach. The second is called as bottom-up approach, and apparently this is also called as Bilode's algorithm. Why it is called as Bilode's algorithm? So if you recall the discussion from the last class, where we tried to correlate the bottom-up approach with how physical pages are allocated to virtual pages when there is a page fault in the context of operating system. So in the operating system, when there is a page fault, so we would like to allocate a physical page to a virtual page. And if there is a free page that is available, then that free page will be allocated to that virtual page. But if that free page is not, but if there is no free physical page available, then we try to evict a virtual page which is mapped to a physical page, that is the one which is going to be used farthest in the future. Okay, so we want to evict uh, the assignment. We want to reassign a physical page that is assigned to a virtual page, uh, which is used farthest in the future. And in the bottom-up approach also, that's what we do. So we start from the first instruction. We start from instruction I1, and we look at, and then we have a free register pool available. So let's say if there are two registers available, so initially, let's say if there are three registers available at this point, let's say we say registers R1, R2, R3, this is the free register pool available. So when we start with instruction R1, we will be able to allocate uh, registers from the free register pool to the virtual registers that are used in this instruction I. And we keep going like that, uh, and we keep going like that. And then what happens is at some point, we may hit a virtual register, and we would like to allocate that virtual register a physical register, but there is no physical register available in the free pool. Let's say at this point in time, there are no free pool registers. So this is free pool registers. So at this point, there is no free pool of registers available. So in which case we have to grab a register, a physical register from which is assigned to some other virtual register before. And so what is which virtual register we will choose to do this physical register reassignment? We pick that virtual register which is used farthest in the future, which is used farthest in the future. The degenerate case here is if there is a virtual register which is dead. Okay, that means it is not used at all in the rest of the basic block, then that means it's a perfect candidate to pick. We just need to reassign that the physical register that is assigned to that virtual register and use it here. So that is the idea. In the bottom-up approach, pick the virtual register, when we say pick the virtual register, we mean use the physical register that is associated with this virtual register, which is used farthest in the future. So this idea becomes important when we study a global register allocation algorithm called as a linear scan register allocation algorithm. So there is one more idea. So this is a summary from last class. This is a summary from last class. Uh, so there is, I would like to present a slightly different view uh, here before. Yeah. So let's say if we have a sequence of instructions. So there is an instruction x is equal to y plus z. Let's say, and then, so if you see the instruction, and then if we have another instruction, w is equal to 2 star x, and then there is another instruction, let's say u is equal to y star z, and then there is another instruction, let's say v is equal to x star w, for example. So here, if you see the set of variables that are live, these are all instructions within a basic block. I just have put an arrow between one instruction to another instruction, and this arrow indicates a program point. If you see the variables that are live at this program point, the variables that are live at this program point are x, y, z. Why is x live? Because x is used here. And why are the variables y and z live? Because they are used here. Okay. And then when we come here, the variables that are live here, again, x is still live at this program point because x is used at in the last instruction. W is also live because it is used here. Y and z are also live um, because y and z are used here. And then if you come down here, if you see at this point, x is still live, w is still live, and y and z are not live because they are not used subsequently in this basic block. And if you just focus our attention within this basic block, you don't even see the use of the variable u within this basic block. So u is also not live. We can just leave it as it is and like this. So if you just look at these three program points, so at these program points, there are three variables that are live. And at this program point, there are four variables that are live. And these four variables, they are interfering with each other. The interfering with each other means we cannot allocate all these four variables the same register. And at this program point, x and w are live. So in order for us to be able to successfully allocate registers to all the variables without spilling, the minimum number of registers required is called as, the minimum number of registers required is 4. So at this point, so we can define something called as register pressure. So at this point, the register pressure is equal to 3. At this point, the register pressure is equal to 4. And at this point, the register pressure is equal to 2. And let's say K is equal to number of available. Let K be the number of available registers. So those program points where register pressure is greater than K, where the register pressure is greater than the number of available registers, so they become problematic cases and they induce spill code. They cause spill. So when register pressure is greater than the available registers, then we have to do a spill. So in the another way of looking at bottom-up register allocator is this, that we start from the first instruction, we keep going as long as the register pressure is less than or equal to K, we are good. When the register pressure is greater than K, we have to pick a register we have to pick a virtual register or a variable which needs to be spilled, and we pick that variable or the associated with virtual register uh, which is used farthest in the future. So this is another way of looking at the bottom-up register allocation algorithm. So in today's class, we will see a slight variation of an extension uh, of this register allocation algorithm when applied at the whole control flow graph level. So most of the so in today's, for the rest of the session, I will be using slides from Mikhail Snish uh, and also from James Palsberg. So let's see how it goes. Okay. Uh, okay. So again, just to summarize, to give a quick picture. So when we think about register allocation algorithms, we kind of, there are local techniques which we have seen till now, that is they work at the basic block level, or they can work within expression level also. And then we will be looking at global techniques which work on a whole function level. Global techniques, they work on a whole function level. And then interprocedural techniques which work on different procedures at a time. So the most interesting, one of the very interesting approaches for global register allocation is by applying a technique called as graph coloring. So what we do is we take the register allocation problem and we construct what is called as an interference graph for that problem. And then we try to do a coloring of the associated interference graph, and from that coloring we can come up with a register assignment to the variables in the program. So this is that is register allocation problem gets reduced to graph coloring problem. So what is this interference graph? It's very simple. So if there are two variables which if their live ranges interfere with each other, so like for example in the previous case we have seen at a particular program point there are four variables which are live at the same time. Then in the interference graph consists of the nodes in the interference graph. They correspond to variables of the program, and there will be an edge between two variables. If there is an edge between, let's say there is a variable x and there is a variable y, and there is an edge between variable x and y, if their live ranges interfere with each other. So if that means if the live ranges interfere with each other, we know that x and y, they cannot be allocated the same register. They cannot be allocated the same register. We will see some examples. So like for example, here in this graph, if you see the live range of the variable x, the live range of the variable x, it starts from this definition point and it goes till this last use. Similarly, the live range for variable y, it starts from this definition point and it goes till this last use. And the live variable for z, it starts from this definition point and it goes till this last use. And t's definition point is here and its last use is here. So here is this is the live range representation. These are the live ranges for different variables. And you can see the live range of variable x and variable y interfere with each other, so there is an edge between them. And similarly, the live range of y and z, they interfere with each other at this point, so there is an edge between them. But if you look at the live range of variable y and the live range of variable u, they don't interfere with each other, so there is no edge between them. So that means we should be able to allocate register R1, for example, to variable y here, and the same register R1 can be allocated to variable u because they are not interfering with each other. So that is the idea. So this is the interference graph associated with this program. And what is the idea? So the idea, so the way so once we have the interference graph, how will, if we want to know, let's say if there are k physical registers available, so we should, if k physical registers, and we know that if we can k color this graph, uh, then that means uh, the original, it is possible to generate it is possible to assign registers to the variables in the program in such a way there is no spill code. And one simple approach, but so graph coloring is a uh, graph coloring, so computing the chromatic number of a graph, that is minimum number of colors required to color a graph, computing that, it's an NP complete problem, right? So what we did is, in order to do, so we started with the register allocation problem and we mapped it to a graph coloring problem. I want you to take a moment and think about it. Uh, so let me first finish this and then I will pose the question. Like graph coloring, it is an NP complete problem. So we cannot hope to find a polynomial time algorithm for graph coloring. So we have to use some heuristics in order to figure out a coloring for the graph. So when we use a polynomial time heuristics, then naturally the coloring that we get may not be optimal, right? So we have to use heuristics. So the coloring that we get may not be optimal. Does this mean that since we are able to reduce this register allocation problem to graph coloring problem, does this mean that the register allocation problem is NP complete? No, so it's not the case. So in order to show that register allocation problem is NP complete, so we have to start with some NP complete problem. Let's say, why not the graph coloring, and reduce it to register allocation. Reduce it to the register allocation problem. So by going from here to here, you don't show that register allocation problem is NP complete. But in order to show that register allocation problem is NP complete, you have to start with an NP complete problem and reduce it to the register allocation problem. And in fact, in 1983, Chaitin from IBM, Gregory Chaitin, uh, I think it is 1981 or 83. So there is a famous paper in which he shows that register allocation problem is NP complete by showing a reduction from graph coloring to register allocation. So the idea there is, if you know what this, if you recall how this reductions work. So here is the space of graphs. This is the space of graphs or set of graphs, and this is the set of programs. So what Chaitin is able to do is, given a graph, he is able to generate a program which maps here, so that if the program that is generated here, if we can find a register location with k plus 1 registers, then the graph that we started with is colorable using k colors. So using that approach, so using this reduction, he came up with a reduction where he generates a program from a given graph. In such a way, if you can solve the register allocation problem, that is, if we can find the, uh, the optimal number of registers for the program that is generated, if that is k, then the original graph that we started with, its chromatic number is, that is, the number of colors required to color that graph is k minus 1. So this reduction shows that our register allocation is NP complete, but not this particular reduction that where we reduce a register allocation to a graph coloring problem. But in any case, for so this result tells us that no, we cannot possibly hope to find a polynomial time algorithm for register allocation. We cannot hope to find a polynomial time algorithm for register allocation. So this is what this result says. But this result, where this particular reduction, it gives us a handle to solve this problem. Okay, so there is a substantial amount of work or so many variations on how to do register allocation through graph coloring, because there are many phases involved, and there are multiple papers, maybe in the 80s and 90s. There is a lot of work on register allocation using different variants of graph coloring. All right. So now let's see the simplest approach, one basic approach in that is that one basic heuristic. I think it is what is called as Kemp's heuristic. Is you start with a so let's say if you have a graph G. So from graph G, this is the original graph. Let's call this original graph, the initial graph, as G naught, and from this G naught we get G1. And how do we get G1? From G naught, you take the vertex with the least degree. You take the vertex with the least degree, and let's assume that vertex has less than k neighbors. It has less than k neighbors. Pick, let's say, so G dash is nothing but G naught minus vertex V. So let's say n of V indicates the neighborhood of V, that is all the vertices which are neighbors of V. And if you look at its cardinality, it is less than or equal to k minus 1. So if you just look at this thing, and then we keep continuing this process. From G1 we go to, and then once we remove V, all the edges that are going out from V, we naturally remove them. And from G1 we construct G2 by iterating or repeating the same process. So one important observation here is, if G1 is k colorable, then G0 is also k colorable. So important observation is, uh, if G1 is k colorable, then G0 is also k colorable. So why is it the case? Because if you see, let's say this is the graph G1, and vertex V is present here, and there are edges going from vertex V to different vertices to different in the graph G. But V has a maximum of k minus 1 neighbors. So if G1 is k colorable, even if each of the neighbors, if they take different colors, they use only maximum of k minus 1 colors, and you can use the leftover color to, you can use the leftover color to color the vertex V. So if G1 is K colorable, then G0 is also K colorable. But then there is a problem. So uh, let's say if we during in this process of reduction, when we move from G0 to G1 to G2, so on and so forth. So you start with G0, you go to G1, you go to G2. Let's say in G2, you pick the vertex with the minimum degree. But if the minimum degree of all the vertices in the graph is K, then we are in trouble. Or is not I don't say of all the vertices. If the minimum degree is K, then we are in trouble. So what we can, in which case, what we have to do is we have to take that vertex and spill that vertex. That means we say that, you know what, we kind of mark it as this vertex is potentially marked for spilling, because there is all its neighbors. You take the vertex with the minimum degree, it's a degree. So at this point, when we are going from G2 to G3, so there is a vertex V. So G3 is equal to G2 minus vertex V. But the problem is, so the neighborhood of V, the cardinality of the neighborhood of V is greater than or equal to K. This is a problem. So vertex V is marked for spill. V is marked for spill. So when we spill it, so all the places where it is used, we can we will spill it. So by spilling it, we will reduce the degree of reduce the mean degree uh, of all the vertices which are in the neighborhood of vertex. And then again, we continue this process from G3, we go to G4. Again, there are two cases. After spilling V, if you look at the minimum degree vertex, its degree could be strictly less than K, or it could be greater than or equal to K. If it is greater than or equal to K, again, we have to mark it for spilling. So let's see how it goes. So this is called as coloring. This approach is called as graph coloring by simplification. So for example, in this case, if you take this example, to start with, you take in this original graph, graph 5 is, sorry, vertex 5 is the min degree vertex. So you remove it and you put it in a stack. Okay, so this goes here. And then after 5 is removed, there are two nodes, 2 and 4, let's say. So now node 5 is, it's not good idea to scratch it. So let me, yeah, so node 5 is removed. So after node and associated edges are also removed. So after this is the graph that is left. So there are two candidates, node vertex 2 and vertex 4, which are of the same degree 2. So what we do is, let's say we arbitrarily break the tie by using vertex 2 to uh, by taking vertex 2 away from the graph. So vertex 2 is put here. So it's put in the stack of nodes. And after vertex 2 is removed, the associated edges are also removed. So what is left is 1, 3, and 4. So again, what we do is, it's any of these vertices, since the degree of all these vertices are the same, any of these vertices are eligible, we can remove them. So we have chosen to remove vertex 1. And then after 1 is removed, 3 and 4, only this part is there. So we can remove 3 or 4, and then we remove 3, and then we have. So what we get is we have this stack of removed nodes, and then the way we do the coloring is we try to, like for example, remember the discussion here: G0, G1, G2. We said if G1 is K colorable, we can G0 is also K colorable. That means in order to color G0, we first want to color G1. Before we color G1, we want to color G2. Before we color G2, we want to color G3. That is, we want to do the coloring in the reverse order. So we start with vertex 4, and let's say we assign it a red register, and after that we include uh, the vertex 3 into the graph to get the previous graph. And and its neighbor is 4, so we assign a blue register to it, and after that we include 1, register 1, sorry, not register 1, vertex 1, and this is the subgraph that we get, and we assign 1 a color which is different from 4 and 3, and after this subgraph is colored, we insert 3. When we insert 3, this is the subgraph that we get, and then after that finally we insert 5, and this is how we do the color. So this is how the whole graph coloring or register allocation by simplification happens. So this is what we discussed. So this idea of spilling. So during simplification, it is perfectly possible to reach a point where all nodes have at least k neighbors. So when this occurs, a node must be chosen, and its value must be stored in memory instead of in a register. This is called as spilling. So and then we remove it from the graph, and then we try to continue with the coloring process. So so there are some so it apparently it seems a node which is marked for potential spill. Later on, it may not be necessary to actually spill it. I'm not exactly sure about the use case, so we will leave that aside. But the big picture I want you to understand here is during this process of graph coloring, if we we could hit a situation where there is a node with at least k neighbors to it, in which case where all the nodes have at least k neighbors, just not one node. All the nodes in the graph has at least k neighbors. So in order to proceed further, we pick one node for spilling, and there are many spilling heuristics here. So this is not what is discussed. So if there are multiple nodes that are there, which node we should pick for, or which variable should we pick for spilling. So these are called as spilling cost or spilling heuristics. So spilling heuristics. Uh, so for example, let's say there are two vertices uh, x and y, or two variables x and y, which are or let's put it this way. This is important. Let's say there are 5 variables in the program. Let's call them as x1, x2, x3, x4, x5. So what the programs does is, what the register allocator does is, it computes the spill cost for each of these variables. So the spill cost, for example, there are two components. Usually we can think broadly. For example, if the variable x1 is present in a loop, then its spill cost should be higher than the variable x2, which is not present in a loop. Because if the variable x1, if we choose to spill variable x1, which is present in the loop, then 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 what happens is as the loop keeps executing, as the loops keep executing, you just keep going and accessing memory again and again and again. So spilling a variable which is present inside a loop is an expensive process. So there is another heuristic, there is another thing to consider. So if a variable x1, if you look at the variable, the neighborhood of variable x1 and the neighborhood of variable x2, so if the neighborhood of variable x1, if it is greater than, if it is, let's say, if it is less than the neighborhood of variable x2, uh, then maybe it is better off to spill variable x2, because by spilling variable x2, you are going to reduce the degree of many other nodes uh, in the interference graph. So there are at least two competing criterion you can see immediately. Number one is if a variable is present in a loop, then its spill cost should be higher, because as the loop keeps executing, so we end up accessing main memory more and more. So let's say if a variable is present in a D-way nested loop, then the spill cost. So let's say the spill cost of a variable x, like for example, we can say 10 power d, that is as the, where d is the depth at which the variable x is present. If the variable is not present in a loop, then d is equal to 0. If the variable is present in a 1D loop, then d is equal to 1. If the variable is present in a 2D loop, then the d is equal to 2. Versus uh, we can kind of put something like the neighborhood of x. That is number of variables that are present in the neighborhood. Because if you spill a variable with a huge neighborhood, then the degree of many other nodes in the interference graph reduces, and it can hugely help us in the graph coloring process, in successfully simplifying the graph as we go down the lane. So we can use some kind of spill cost strategy such as this. And whenever we end up in a case like this, we can compute the spill cost and decide based on the spill cost which variable we should spill. Okay, this is what is called as a spilling heuristic. Let's keep going. There is one more interesting idea that we have to keep, when this kind of occurs again and again in register allocation, that is coalescing. So if you see the variable y here in this particular case, variable y goes from here to here. Its the definition point is here, and its use point is here. This is the last use, in fact. And if you look at t, its definition point t is here, and its last use is here. So if you look at the corresponding interference graph, the variables y and t, they don't interfere with each other. But then if we allocate, like for example, variable y register R1 and variable t also register R1, since they don't interfere with each other, so we will be able to eliminate this copy instruction. Whatever the value that y that is present in y, we can just compute, we can just reuse it for the variable t, and we can eliminate this copy instruction. So wherever, so there is no, wherever there are two variables uh, where there is a possibility for coalescing, we can kind of put a dashed edge between them in the interference graph. They don't interfere with each other, but it would be good to kind of merge them. So that is, we kind of treat y and t as the same variable. From y and t, we can create a new variable yt by merging them together, and we can allocate the same register RT to both of them. Same register, whatever it is, to both of them together. So this is the coalesced interference graph. But then coalescing is not always recommended. So due to coalescing, sometimes the degree of you may end up increasing the degree of many other nodes in the graph, and that could lead to making the graph non-k colorable. So because if you make the graph non-k colorable, you will end up what do I say, uh, inducing spill generating spill code. So we want to do coalescing in such a way so that we don't cause adverse effect to the interference graph. That is, for example, you don't you don't make the graph, the resultant graph, k colorable, for example. Okay. So this is one thing which keeps, wherever you see register allocation algorithms, this coalescing thing keeps coming again and again and again. So uh, make a note of this. So, and one more important idea is what is called as a live range splitting. So if you see here, uh, if you see the variable x here uh, in this uh, in this example, the variable x live range, the definition point is here, and the last use point is here. So the live range of the variable is the whole thing. And so what you can do is you can and because of that, the variable x interferes uh, with variable y and variable z, so the graph is not too colorable. So you have to generate spill code, so on and so forth. And this kind of thing can happen either from the code, or because when you try to do copy propagation and some other optimizations, what can happen is, if you recall the discussion maybe a few weeks back when we were talking about impact of compiler optimizations on the intermediate representation, there is one particular example wherein as we kept improving the IR by eliminating redundant computations, we kept increasing the live range of one particular variable. But in any case, so so what we can do, for example, but if you see in between, the variable x is not used at all. So what we can do is we can split the live range, okay, of variable x and into two parts, and then we can do register allocation for these two different live ranges independent of each other. So live range splitting is one particular technique that will be used in uh, in register allocation algorithms, to so that the graph becomes so that it is possible for us uh, to to do register allocation without by spilling minimal number of registers as possible. Sometimes it is necessary that some variables have to be kept in some registers because of the constraints from target, because of either the application binary interface constraints, or like for example, if you look at the arguments to a function, a particular ABI says the arguments should be residing in registers R1, R2, R3, and the result should be present in register no R10, like that. So there could be constraints either that are emanating because of the ABI, application binary interface specification, or because of the target processor constraints. And we kind of take care of it, taking the actual complexity in real register allocation in production quality register allocation in production quality compilers is taking care of all these constraints in a nice way becomes easy. When we try to study algorithms at this level, they look very clean, but when we try to implement it at a in a real compiler, they becomes dirty because so many other nasty details come in, and we have to respect all those constraints. So now let's move on to the linear scan register allocation algorithm. So, so linear scan register allocation algorithm, as I said, it's a kind of an extension to the bottom-up register allocation algorithm that we have seen already before. So the good thing with the linear scan register allocation algorithm is it's a very fast algorithm, and because of that, in JIT compilers where we would like to do on-the-fly register allocation, that is, you are interpreting a program, and then you check that this particular function is being called again and again. So you would like to translate the bytecode or the IR of that program into native code, and so because of that you want to do register allocation, and you don't want to spend lot of time in the register allocation because you are doing it at runtime. So you want to use a fast register allocation algorithm. So their linear scan register allocation algorithm really helps. So the idea here is very simple. Let's say the live range of variable of different variables in a program text is like this. I just want to make one point here. So let's say if your program has, this is instruction I1, this is instruction I2, I3, I4. These are the sequence of instructions in the program I5, I6, I7. So let's say you have something like after I4, so I4 is a go-to instruction to I3. So essentially this is like I3, I4. I did the numbering wrong. I4, I5, I6. So let's say, so this is a sequence of instructions, and these two constitute basic block B1, and these constitute basic block B2, and this constitutes basic block B3. So let's say if you consider variable B, so let's say instruction I4 can be something like this. Instruction I4 is U is equal to something like B plus C. So if you see that instruction, the variable B, we consider variable B is live even at instruction I5, because if you go back, there is a path starting at this program point. B is still live because there is a path from this program point along which the variable B is used before it is being defined. So because of that, we think of the variable B is still as live at this particular program point. So when you take code and when we try to look at uh, try to check what are all the program points at which the variable B is live. So don't get fooled by the fact that the last use of the variable B as it looks from the text is at this point. Because of that, variable B is live only till this point. It's not true, because you have to look that there is a backwardage because and there is a path from this program point along which the variable B is used before it is being defined. Let's see, there are some questions, it looks like. Okay, I'll take your questions in a moment. So, yeah, so and then these live ranges. So, yeah, so what happens is this is how you compute the live ranges of different variables in your program. So what happens is you start with variable A. So variable A is there are, let's say the machine has two registers. You allocate variable A register R1, and at this point you encounter B. You allocate variable B register R2, and at this point you have variable C, and variable, there are only two registers available, and so you spill variable C. C, you cannot allocate a register to variable C, so you spill the register, the variable C, that is C is we keep it in the memory. And then when we go here, so yeah, so variable B is present in register R2 as it is. And then at this point when we come here, so you see variable D, it is defined here, and we see that there is an empty register R1 that is available, so we allocate register R1 to variable D. So this is one example of linear scan register allocation. But then there is one thing that we can do here. So if you see here variable C, it could, I think it is possible for us to kind of have a spilling strategy where we can say, you know what, A and B are allocated registers, but we can possibly spill a register which is already a variable which is already allocated a physical register by picking that variable which is used farthest in the future. So we can possibly do better than the simple approach that we have taken here. I think that is what happens in the real linear scan register allocation algorithm. But we don't have time to get into those details. But this is the big picture. So you construct the live ranges and you scan the program, and when there are free registers, you allocate them. When there are no free registers available, so you kind of spill the variable which is demanding for a register, or the other approach is to uh, or the other approach is to spill an alternate variable which is assigned a physical register based on certain heuristics, such as spill the variable which is used farthest in the future or something like that. All right, so this is a quick summary about the linear scan register allocation algorithm. You will find this algorithm in LLVM, and in many compilers this algorithm is implemented. In order to close this discussion, I want to make one important point. Uh, yeah, so let me, that is, when we have seen that so Chaitin proved that like register allocation is uh, is NP complete by reducing graph coloring to register allocation. But what happens is, and then so that doesn't mean anything about that doesn't say anything. Uh, so what I'm trying to say is, but then what we have is what we tried to do earlier is we took the register allocation and then we came up with the interference graph. And then we wanted to, so we take, yeah, let me take a moment and I'll just take couple of more minutes and I will conclude, because there is one important point I want to share, and then we will take a break. So what is the idea here? So you take, what is the approach that we used in register allocation using graph coloring? So you take the program P. From the program P, you generate an interference graph. And then you try to color this graph. But the problem with this coloring this interference graph is it's in an optimal fashion is it's NP complete. So it's no, we have to come up with a heuristic. But it so turns out, if you take this program and convert it into an SSA form and then construct an interference graph, then we get then the associated interference graph turns out to be what is called as a chordal graph. So in chordal graph, so it doesn't have 4 cycles. Like for example, if you take any subgraph of chordal graph, it doesn't have a cycle like this. So always there will be a chord which kind of finds a short circuit in any cycle which is of length greater than 3 in that chordal graph. And it seems there is, if the graph is a chordal graph, then we can color that graph in polynomial time algorithm. So polynomial time graph coloring algorithm exists for chordal graphs. So this is the most important idea. So this is a there are many interesting papers here, but what I want you to take a note here is if you start with the program as it is and we construct an interference graph, then we cannot solve the graph coloring problem in an optimal fashion because graph coloring is NP complete. But then if you translate this program into an SSA form and construct a chordal graph, then the associated chordal graph, so the associated interference graph, it has some nice properties. Because of that, it is possible for us to construct a polynomial time algorithm for coloring that chordal graph. So maybe I will post one or two resources on the course website uh, sometime, so that those of you who are interested in looking at what is happening here, you can get a deeper insight there. That's all I have for you today. Uh, so, couple of important announcements.